Hi, I'm Bill Hanson, and I'm going to tell you about how I forged a chain of solutions to help solve subset sum problems using two AI approaches of dynamic programming and backtracking. It's a basic it takes the form of a basic number puzzle, and so the question, what stays, what goes? So we've got our number puzzles here. We've got the targets for the column. That's what we want the columns to sum to. Got the row targets here, and then the uh, simple problem, relatively simple problem, is to basically just leave behind the numbers that add up to the appropriate rows and columns as we see. So we want to find the correct subset for the correct sum in each case. But this is more than just a puzzle. This is the subset sum problem is a piece of what's known as the knapsack problem, which is a very well-known problem in AI, where you've got a set of objects of various sizes, shapes, and weights that you have to maximize the number of which you can put into a knapsack. And everybody who's packed their suitcase for a trip knows exactly how this works. And so because this problem was originally thought to be NP hard, it became the basis for one of the first public key crypto systems. It was broken in relatively short order, and we'll talk about exactly why that is. But this is still used today for complex financial auditing. And if you think about, these huge companies who've got financial documents with hundreds of thousands or millions of numbers, some very large, some very small, and you've got multiple subset sum problems on every single page, then a whole lot of work being done with this. And of course, this also works in as far as job scheduling and resource allocation. So this is a very important program, both as an AI problem and as a practical problem. And so we could sure brute force this, but as we see, this problem gets exponentially large in a big hurry. And so one approach that I chose is called dynamic programming. And basically the thing behind dynamic programming is you don't need to solve the problem all at once. All you have to solve is little piece parts of it until you finally get enough of them put together, then you can build a larger solution. And so just a very simple example. So we've got these four numbers that we want to see if they sum to 9. Notice our number line doesn't go past 9 because we don't care if the numbers sum to 10 or 12 or 14 or whatever. All we want to know, do they sum to 9 or less? And then we can use those to see if we actually do have a valid subset sum problem, which of course we can see readily by inspection, but still. And the way this works is at each spot, the algorithm asks itself, okay, can I make a 3 using this 3 by either leaving it in or leaving it out? And in this case, we leave it in so we can make a 3. But we can't make any of these other numbers because all we've got is 1, 3. And so that's all the algorithm cares about right now is that, yeah, we can make a 3. The same thing here. Again, we ask ourselves, can we make a 3 by using the 4 or by leaving it out and using the 3? And the answer is yes. We can do that. And so again, we're solving this thing one tiny piece at a time. We can make a 4. And of course, we can add both of these things together to make a 7. And so we know what these are. And again, when we get to 7, we can make a 4 by either keeping the 4 and leaving the 7 out. But either way, it's true. And similarly, we can make a 7 as well. Again, we don't care if we can make these add to anything else. All we care about is, can we make a 7? And so then when we get to 2, we can say, okay, 2, we can make a 2 with a 2, but we can also go back, step backwards 2, up 1 to the last number, and lo and behold, 2 plus 7 equals 9. But the important thing is that we never worried about whether or not the numbers sub to 9 up until we got to this very last stage. All we wanted to know is whether or not we had something that we could add to 2 and make 9. And so because of this, this is a very fast way of solving row and column based problems. And by I mentioned earlier that this problem was thought to be NP-hard, uh, but by using this divide and conquer kind of algorithm and dividing it up by rows and columns, they're actually able to solve this problem in pseudo polynomial time, meaning that they readily broke that early cryptanalysis algorithm uh, by using this dynamic programming approach. But there's another way we can think about this problem too, and we can cast this problem rather than as a set of rows of columns. We can say, okay, what this really is a constraint satisfaction problem, right? We've got row constraints, we've got column constraints, and then as this animation is showing, what we're doing is we're testing, backtracking, retesting, and gradually stepping through this. And so what we've done is we've taken this grid here and we've treated yet each spot as a binary decision, trying again like we did with dynamic programming to either keep it or to drop it. And again, backtracking to the last good state. This works really good, but it's really slow. I mean, really slow. And you know how slow you might ask. Well, let's look at these numbers here. On the top, we're looking at speed, but on the bottom, we're looking at capability. And partitioning by rows and columns is really fast. Like I said, we're solving these fairly large numbers in about, in matters of a hundredth of a second. Whereas, and you can see this is a logarithmic scale here, by the time we get to puzzles that same size, we've gone from 2/100ths of a second to greater than 83 seconds. And, it's going to go nowhere up. But because we've treated each of those, 400 spots as a binary variable, the state space is suddenly exploded to 2 to the 400th. And so, wow, that's a problem. So we could say, well, shoot, let's just go with the fast one. But the trouble is that the puzzles get larger, they become messier, having more solutions, and as we get more solutions, then the ability of a row or column-based approach to solve this decreases in a big hurry. And so, for example, using the size of puzzle we looked at on the last slide, a dynamic programming approach can only solve about 23% of those puzzles. By the time we get to 400 spot puzzles, the dynamic programming approach can only solve one or less than 1 in 1,000. And so the question I ask myself, can we combine this? Can we make a hybrid approach that makes the best of both worlds? And I think that answer is true. That we, instead of looking at the individual numbers, what we do is we treat each set of valid number sums, as a vector. And then instead of trying individual numbers, we try a vector. And like this little stylized animation went, we basically laid one in, we checked it, didn't work, we backtracked, then went back, and then finally we were able to fill in the grid. And so I think that by adding the speed of a dynamic programming with the robustness of vectors and backtracking is going to give us a heck of a good way to do it. Unfortunately, I couldn't get it done in time for the project, but I truly think that this is a really interesting direction for the future. So my lessons from beating and sometimes beating my head on the forge is that faster is not always better, because as the problems get bigger and messier, then the fast approaches can't deal with the complexity and the uncertainty of that. And then one of the big lessons is that the way we structure that problem, how we subdivide it, and how we attack it strategically really matter. It makes a huge difference whether we just go with a backtracking approach or if we try to partition it smartly. And just like in life, our ability to self-correct, backtrack, come to a new path is absolutely critical. And I think we've learned from these problems, and I think that we can really forge a new path in solving these kind of problems for the future. Thank you.